A red warning polygon covered northeastern Arkansas. Later, the tornado map held no confirmed track there. On the evening of April 15th, 2022, the National Weather Service office in Little Rock issued a tornado emergency for southeastern Randolph County and central Lawrence County, including Walnut Ridge and Sedgwick. The warning described a large and destructive tornado indicated over Walnut Ridge and moving towards Sedgwick. Radar indications and spotter reports supported that escalation. That sequence matters. First came a storm whose radar presentation indicated dangerous rotation. Then ground reports added support while the circulation approached communities inside the polygon. The emergency joined those separate signals into one urgent claim about location, motion, and consequence. At that moment, the warning was not trying to write the storm's final history. It was marking the area where the available evidence indicated the greatest immediate danger. This was not a vague suggestion buried in a forecast. A tornado emergency communicated an exceptional and immediate threat. Yet after the storm, survey teams investigated the warned area and found no confirmed tornado touchdown, tornado path, or associated tornado damage. The warning record said, "destructive tornado." The ground record did not verify one. How could the evidence point so strongly in one direction, then leave no confirmed tornado behind? The answer begins inside the red polygon, with the radar beam crossing it. Weather radar does not look across the landscape like a camera. It sends pulses of energy into the sky, measures what returns from rain, ice, hail, and other objects, and compares motion toward and away from the instrument. Closely packed opposing motions can indicate rotation inside a storm, but rotation inside a storm is not yet proof of a tornado touching the ground. The radar and the threatened communities also occupy different places. A beam leaves its antenna at a slight upward angle. As it travels, the curved ground falls away beneath it, and the beam widens into a larger slice of the atmosphere. Picture a flashlight aimed just above a long, curving road. Nearby, its light reaches close to the pavement. Farther away, the beam hangs above the cars and illuminates a wider area. Weather radar has the same basic geometry. It may sample organized rotation aloft, while the crucial surface circulation remains below its view. That turns the warning polygon into a two-level problem. Above the ground, radar can reveal meaningful motion across the storm. Beneath that sampled volume sits the question the warning must answer. Has the rotation tightened all the way down into a tornado? Distance also changes the contents of each sample. A widening beam can gather returns from rain, ice, hail, and other material within the same volume. Modern radar compares those targets in more than one orientation. One useful product is called correlation coefficient, which helps show whether the objects in a sample behave alike or form a disorderly mixture. Tornado debris is disorderly. Leaves, boards, insulation, and fragments of many shapes can lower correlation coefficient. When that lowering sits beside strong rotation, it can support the interpretation that a tornado is lifting material from the ground. Hail creates the next reversal. Large pieces of ice can also lower correlation coefficient and produce unusual radar behavior. Hail may create an artifact called a three-body scatter spike, where radar energy follows a longer path involving the hail and the ground before returning to the instrument. The display can therefore contain strong rotation and complicated targets without providing a simple label that says hail or debris. That ambiguity matters to the Arkansas case, but it does not solve it. Hail could complicate interpretation. The surviving evidence does not prove that hail caused a false debris reading or caused this tornado emergency. It was one limit on the view, not a single mistake, that explains the outcome. The radar evidence leaves the first question partly open. Rotation was indicated, but had it reached the surface? The answer then depends more heavily on observers beneath the storm. That evening, darkness and precipitation limited visibility. Spotter reports contributed to the warning decision, but the supplied record does not establish exactly what each observer saw. The ground view was urgent and incomplete at the same time, just as the radar view was broad and potentially elevated above the surface. Now the polygon connects both vantage points. Radar samples motion and mixed targets in the storm. Spotters provide information from below. Each source covers a weakness in the other, but their overlap may still leave the near-surface circulation obscured. Was the unusual radar return hail, tornado debris, or some unresolved mixture of signals? The available evidence could raise concern without closing that question. This is where explanation becomes a decision. The storm is moving. Radar scans update. Reports arrive. Waiting for a perfectly clear surface confirmation can consume time available for protective action. Escalating to a tornado emergency on ambiguous evidence carries another cost because the language is reserved for an exceptional threat. The warning cannot eliminate either risk. It must cross a threshold before the storm has finished and before the ground can be inspected. In northeastern Arkansas, radar indications and spotter reports pushed the decision toward the higher warning. The polygon appeared while the evidence was still arriving. Only afterward could the decisive inspection begin. National Weather Service survey teams investigated the warned area. They did not confirm a tornado touchdown, a tornado path, or associated tornado damage. That absence did not erase the rotation seen during the storm or make the spotter information imaginary. It changed what those earlier signals could prove. The survey result forces every earlier clue back into question without declaring it worthless. Rotation still described organized motion in the storm. The spotter report still contributed a ground perspective during poor visibility. Hail still offered a way for mixed targets to complicate the radar picture, but none of those pieces, alone or together, left the physical confirmation that would turn the emergency's tornado description into a verified tornado record. This is the collision at the center of the story. The emergency was justified by a developing threat that instruments and reports indicated in real time. The later survey could judge the finished storm against physical evidence. What looked like one confident claim on the warning map became two different conclusions separated by time. If this kind of evidence-first weather story is useful, subscribe to Eyewall Stories. The warning asked what danger had to be communicated before the next scan and report arrived. The survey asked what the storm had actually left on the ground. Those questions run on different clocks. During the warning, every new scan could sharpen the picture, but waiting for it also allowed the storm to move farther. Every report could add a missing surface view, but darkness and precipitation could keep that view incomplete. The warning clock shrank while the evidence changed. The survey clock started after that race was over. This timing explains why a crisp warning does not require crisp knowledge of every layer of the storm. A polygon has sharp edges. Radar colors occupy exact places. A phone alert arrives as a firm block of text. Communication has to convert a shifting three-dimensional atmosphere into an action people can understand immediately. The map is clean because the message has to be clean. The atmosphere is not. That distinction protects the story from two tempting but unsupported conclusions. The missing tornado track does not prove the real-time signals were invented. The warning does not prove that a tornado secretly touched down without leaving confirmed evidence. The surviving record supports concern, followed by non-verification, and it stops there. The hidden physics makes that boundary visible. High above the curved ground, a widening radar beam samples a broad volume filled with wind, rain, ice, hail, and other targets. Beneath it, observers face darkness and precipitation. Between those views lies the surface circulation that determines whether rotation in the storm has become a tornado. Radar geometry explains why that layer can remain poorly sampled. Hail explains why unusual targets may demand caution. Limited visibility explains why ground reports may not settle the picture. Together, those limits explain how an exceptional warning decision can be reasonable, even when the later survey cannot verify the tornado it described. Return to the red polygon over northeastern Arkansas. During the storm, it marked where a large and destructive tornado was indicated, and where an exceptional threat had to be communicated. After the storm, the tornado map held no confirmed track there. One map preserved what had to be feared in time. The other preserved what could finally be verified.